So I don't know, do I even need to film these anymore? Who said yes? Sarita? Was that Sarita? Was it Hammond ad? Never mind. All right, guys. Remind me here. We went over a couple examples from 8, right? Okay. So this is maybe redundant, but I'm going to go over one quick little example from 9. Solving a system by graphing. Let me do a more funky one. Okay, so I'm not going to do a ton of examples of this because it's something we've already done quite a bit. So this is a slightly different setup here. So say you're looking for a pair of XY values that satisfy both equations. So what you're going to get in these cases is a lot of times maybe 1, maybe 2, maybe 3 discrete points, like individual points that work. And then in a few minutes, we're going to talk about ones where you actually start to get more like big collections of points that work. So for now, we're looking for a couple discrete points. So the technique here to solve by graphing is to first write them in a form that looks more familiar for graphic purposes. So what that would look like would be taking this top one and rewriting it like that. So algebraically speaking, what you're doing is subtracting x cubed from both sides of the equation. And how about this guy? Add the x over. Are we okay with that? Mm-hmm. So if you did, say this question was more like number 11, and just said, how many solutions are there to this system? All you'd have to do is draw a real rough sketch. Here's y equals negative x cubed, and here's y equals x plus 2. So if you're just drawing a rough sketch, you can see there's only one solution to the system. And what kind of x value is it?
Negative.
Negative, and the y value is positive. Now I'm giving you a grid on your paper there, so really all you got to do beyond that is just graph it a little bit more carefully. And if you do that, you're going to see the answer appear as clear as day. So maybe name some points on this curve here. Well, points like 0, 0, 1, negative 1. So if you just graph it kind of carefully, there's the point that really has our attention, hopefully, because that point also is on the line. So if you graph the line really carefully and you graph the whoop-de-doop-de really carefully, you're going to find that they cross at negative 1. So let's interpret those numbers. Negative 1 is the x value, and positive 1 is the y value. All right. Do we all agree that that's pretty straightforward?
Yeah.
Not too hard.
Yeah.
Number 10 is the same idea. Those should all be things that you're more or less comfortable with graphing without having to rely on a computer. 11, same way. Again, you might need to modify it a little bit, but it all comes back to those basic parent functions we've talked about. Maybe those parent functions could be shifted left or right, up or down slightly. But. All right, are we okay to move on, or are there any questions on this idea? Mm-hmm. Okay. All right, let's get into something that may be new, possibly. This is another thing that I'm guessing some of you covered this last year, some of you didn't. All right. So 12. Let's look at 12A to begin with. So the first thing you might notice when you look at this is it says graph the solution set for each inequality. So what is that? What do you mean the solution set? Well, let's start with a basic. Don't even think about graphing quite yet. Who can tell me a pair of XY numbers that satisfies this?
-2 and -2.
Very good. X can be -2, and Y can be -2. Why? Because if you add -2 plus -2, that is less than 2. Okay, let's put a couple more on there. Anyone else got one? 0, 1, great. Anyone else? -2 and +2, okay?
-500 and -300.
Yes, that's good. I'm glad you said that because yeah, like even numbers that are really extreme can work. I'll throw one of mine on here. How about the number 0.36279 and -4.993026?
Yeah.
So what's the point of that? Well, we're not restricted to integers, right? Now this might give you a hint. How many points are there out there that satisfy that? Right, an infinite number. So infinitely many points that work. So what that tells us is we're going to have to we're not going to be able to just like put dots down to say there's a solution, there's a solution. We're actually going to be shading in like a big space of solutions, okay? Now, of course, let's real quick throw in just one or two that don't work. So some points that don't work, well, it's not hard to come up with one. How about 7, 2? How about 18, -3.7718? Get the idea. It's very easy to come up with a pair of numbers that don't satisfy that. So last thing I want to talk about, don't worry, we're not going to do this on every single question. This is just for the first one we're looking at. How about set of points that are kind of borderline? How about the set of points that would satisfy this? Where you're not quite above 2, you're not quite below 2. So how about a point 1 and 1, 0 and 2? How about 6 and -4? So there's going to be a whole, now if I listed out it would be physically impossible, but suppose I could list out every point that satisfied that, what shape would it make? A line. A line. Now, the way we denote this is, now, by the way, when you're doing these in practice, what you're going to do is take that and think of it like, those are the same, right? So what you're going to find is you have this boundary, this line, where if a point, so what does a line do to the plane? Well, a line splits the plane into 2 halves. And so what you're going to find is some points are solutions, some points are not solutions. And what's the dividing line? It's this line right here. Okay, so what you're going to see if you say test out, okay, here's 0, 1, that is in the good zone. So this is the zone, this whole region here. This is me trying to shade. You've got, if you have lit shading skills with your pencil, that's great, but you can just draw some lines to indicate any point that lives below that line is going to be a solution to our original inequality. All right. Do you guys feel like you understand the general idea here?
Yeah.
Do you or do you not?
No,
Yeah.
it's
I understand though, man.
Wait,
But how it works on the
you
sea.
do like the dash line when it's like not equal to?
That's a good thing to point out. Look at this. If this had said x plus y is less than or equal to, then every point on this line would be a solution. And we'd indicate that with a solid line. But since the point, say 6, -4, way over here, that actual point isn't a solution, it's on the dashed line. But you could go slightly below it, like the point 6, negative 4.1 is a solution. So that's what the dashed line indicates. So thanks for mentioning that. I want to go over the one right below, 12C, is pretty interesting.
Does it mean it's a solid line when you have like a line underneath?
Yeah, so yeah, if points on the curve are solutions, it's a solid line. All right, the answer to 12C may surprise you. It's pretty likely it will surprise you.
The answer may be surprising.
So, all right, first thing you're going to do is to draw the curve of what set of points makes y equal to this. Hopefully we all know what that looks like. It's the square root curve shifted what direction?
Left.
Left.
It is half birdie.
So you're on your grid, it should look something like that. All right, so can someone throw out a point that does not satisfy this?
-2,
Oh, okay, you're getting to the heart of it right away. So -2, 4 does not work. Let's see, why is that? Well, is 4 less than or equal to the square root of -2 plus 1?
Can't do it.
That first of all is a very weird statement. Is 4 less than or equal to an undefined quantity? Well, we can certainly say that if this is not a true statement, okay? So a point like -2, 4, like way up here, is not going to be in our zone. So you can rule that space out there. I was thinking maybe like, how about plugging in, sure,
1,
2.
1, 2, 2.
Let's try plugging in a point like, how about 2, 3? And see if that works. Is 3 less than or equal to the square root of 2 plus 1? Is that true or false?
Yes, no, it's bigger than.
Yeah, 3 is not smaller than its own square root, right? The square root of 3 is like 1 point something, right? So this is not true. So 2, 3 lives up here, right? So this point, no. This zone, bad, right? Now, I'm definitely interested in this zone here. So how about a point like, I don't know, how about 3, 1? True or false? Is 1 less than or equal to the square root of 3 plus 1? Yes, that is true. That tells me that, here's 0.31, this zone is good. But wait, how about points like down here?
No.
Do those work? Let's try one out. How about a point like 3, -7? A point way down here. Does that satisfy this equation? Let's try it out. Is -7 less than or equal to the square root of 3 plus 1? Is that a true statement or a false statement? That is true. So that tells me is actually any point down here also works. Okay. And then how about, there's an interesting boundary over here. So Aiden gave us sort of a clue. When he plugged in -2, it rendered this side undefined. So there's actually going to be a boundary right here. X cannot be to the left of -1. So what you're going to have is this idea. So for example, let me pick a point like here. Does this point satisfy this equation? The point -1 -2. True or false? -2 is less than or equal to the square root of -1 plus 1. True or false? True. Make sense? So what that tells me is that any point that lives on this vertical line, any point who has an x value of -1 and a negative y value is going to work out for us. Okay? And then like we just showed earlier, all of these points also are going to work. So it turns out that it's actually this weird slice of area. Now, someone often will point out here, wait a second, that's not a function anymore, right? This curve that I've drawn is not a function, right? It fails the vertical line test. But that's okay, that's not a problem. We're not trying to graph a function, that's not our goal. Sometimes we get confused, we think, oh, our goal is to graph functions. No, our goal is to represent the set of points that satisfies this statement up here. Any point on this vertical line here, I guess technically it's a ray, but any point on this vertical piece here works, any point on this curve works, and any point trapped over in this shaded in zone works. How do we feelies about that?
I don't like it, but I understand.
You don't like it?
I don't not like it. Get a shoe. Get a color. I like colors.
Hurts my feelings.
All right, I want to do one or two more with you. Look at the next page, and look at the top two. You're such a lit savage.
Will be one.
You are totally correct, Dale.
Before.
Although, Nikita, here, I'll hit you with one of these. The first one's actually not a circle. It's a disc. Because we're going to end up, we're not just going to, because a circle is this one-dimensional object of points. We're actually going to have a two-dimensional surface of points. So I just wanted to do it actually to you. So. Okay, so 13A. Nikita has pointed out that she's like, yeah, this is about circles. That's totally correct. Because suppose I wanted to start off with the question of what pairs of xy points satisfy this equation. Hopefully you recognize that. That describes a set of points that form a circle. Okay, what's the radius of that circle? 4, very good. Remember guys, the form is x squared plus y squared equals the radius squared. If you see that form, it's talking about a circle. How do I get the radius? It's going to be the square root of that number. So, if you're trying to draw a circle on a grid, my advice is just to draw the top, bottom, left, and right dots, and then just try your best to get an arc that looks reasonable. This doesn't have to be perfect. Okay. The interesting part, though, is this is not the answer to the question. If the question had said what points satisfy this equation, we'd be done. You have to live on this circle somewhere in order to satisfy this. But the question's asking actually for the set of points that satisfy this. So how about a point like 1, 2? Does 1, 2 satisfy this? Let's see. The nice thing is it's easy to check. True or false statement? True. So the point 1, 2 right here is actually in, by the way, this circle split the plane up into how many zones? 2. Inside and outside, right? So originally I had this big plane. It might makes more sense if I imagine the big plane like this, no axes, and I draw a circle. Well, okay, either you're in the circle or you're out of the circle. You don't have to be one. So anyway, 1, 2 works. So I'm going to shade in this. And then think of any point outside the circle and ask yourself, does that point satisfy the inequality? For example, a point like, I don't know, 5, 3. 5 squared plus 3 squared is not less than or equal to 16, so that's a no. So 5, 3 way over here does not work. All right, so anyway, if you're wondering, that's called a disk. Okay? Because the set of points forms a solid two-dimensional surface whose boundary is a circle. All right. One last one with you. Compare that to B. The set of points such that x squared plus y squared is greater than 4. First order of business. What's the radius of the circle? 2. What kind of, how am I going to draw this circle, you think? Dashed. Good. Let's try your best to make the dash circle.
Say them naturally occurring.
I made a pretty good rhombus.
A rhombus. Okay. So you should have a circle of radius 2, but it's a dashed line because, for example, the point 2, 0 does not actually satisfy that. It gets very close, but it's not quite satisfying it. And that's because it's missing the little. Okay, again, pick a point in one of the zones. So I don't know, the point 3, 2, why not? 3, 2. Is 3 squared plus 2 squared greater than 4? Yes, it is. So we're actually then talking about this region outside the circle, which you might refer to as like, I don't know what shape is that. It's kind of like the, huh? Kind of. It refers to the set of the entire plane, the entire Cartesian plane, except for a disk. So they'll refer to that sometimes as like the complement of a disk. Oakley dokley. I hope that. Oh, thanks for the 100 bits.
Why did that?
Oh, thanks for the 10 gifted subs. Wow, we're doing great.